Alright, just a few sections left for the semester, and Chapter 4, it starts to kind of build a little bit, and I took some sections that were long sections and made them into a couple short sections. This is one of the sections that was attached to another section that I just kind of turned into its own short section, so I'm not expecting this to be a long lecture. And I'm teaching it differently than I would normally teach it, just because this concept, for some students when it came to the tests, didn't really, they do that well on it. So I trying a different approach. So there are other ways to do the problems in this section, and if you don't like the strategy that I teach in the video, just come visit me and I can show you how I normally teach it, and you might find that better. I think for me it's easier the way that I do the problems, but for most students it just wasn't easier. So there are other ways, and if you don't like what I do, just come visit me and I'll try to show you another way. So this is an OR problem section. We'll do AND problems at some point, but for OR problems, the thing that makes a problem an OR problem is that it's a single experiment, like for instance picking one ball out of a jar, or rolling a pair of dice once, or picking one card from a deck of cards. So it's a single experiment, and it's an OR problem if success is determined by one of two events, one event or another event happening. So we need so this experiment is called, successful if one event or another event happens, hence the OR problem. And in most all OR problems, you'll see the word OR. If you don't see the word OR, it's probably not a OR probability problem. Here I write, sometimes we'll see the words at least, and it's an OR problem. I think most of our problems in this section are going to have the word OR to make them clearly an OR problem. And when we get to the test, you'd like to think I use the word OR to make the OR problems really evident. And in this section, I'm going to solve all the problems with a formula. And the OR formula is essentially this. So it's the probability of A or B is the probability of event A plus the probability of event B less the probability of A and B happening simultaneously. Again, that formula won't make a lot of sense right now until we get into the problems, and as we get through the problems, I'll try to tie the problems to the formula. I'll make evident why something's an OR problem, and then just kind of make the section kind of fit the formula and fit the definition. So first example, suppose we roll one dice. So it's just one dice rolling it one time. So this is the beginnings of having the chance to be an OR problem, because in an OR problem you're doing a single experiment, and this is a single experiment. I'm rolling one dice, and I'm interested in finding the probability of rolling an even number or a number greater than 4. So this completely fits an OR problem. It's a single experiment, and success is determined if one or another event occurs. And so success here is if an even number occurs or a number greater than 4 occurs. So this is a classic OR problem. I'm doing one experiment, and I'm allowed one or another event to occur, and this experiment would be considered a success. So it's completely an OR problem, and in an OR problem we can use a formula to solve a problem, and the formula that we're going to use to solve OR problems generically is the probability of A or B equals the probability of A plus the probability of B less the probability of A and B happening together. And that's just too generic in terms of being able to solve, word problems, because those A's and B's aren't going to appear in most of the word problems. So somehow we need to make our problem fit the formula, or make the formula fit our problem, one way or another. But at first I'm going to make our problem fit the formula, and then I might start making the formula fit our problems once we get more used to it. So if I wanted to write this question in a more proper mathematical notation using P for probability, so I'm supposed to find the probability of getting an even number or a number greater than 4, I've changed the problem and I've rewritten the problem to this. So this right here, to me, says find the probability of getting an even number or greater than 4. So this whole part of the problem from here to here has the same meaning as this symbol. So find the probability of rolling an even number or a number greater than 4. That's exactly what this says. Find the P means find the probability, and what am I finding the probability of? Getting an even number or a number greater than 4, kind of in a really kind of simplistic symbolic notation. So to make our example fit the formula, well, the formula has a probability of A or B. So I see the or part, but I don't see the A or the B part. So I'm going to get an A or a B part by making A the probability that an even number is rolled. So if I wanted to consider this the probability of A or B, well, A would have to be the probability that an even number is rolled, and B is going to be the probability, or the event, I guess, that a number greater than 4 is rolled. So I'm separating the two events that are described in the problem, rolling an even number, assigning one of them A, and rolling a number greater than 4, assigning one of them B. So I'm making my problem, first of all, I made it started off in words. I translated it to symbols that were closer to the symbols that I see in the formula, and then I'm assigning the events letters A and B. Now I can make our problem fit better the formula, and I'll try to write this bigger. So instead of, so where we have the probability of A, I'm going to change that to the probability of getting an even number. And where we have the probability of B, I'm going to have that changed to the probability of getting a number greater than 4. So the formula says the probability of A or B. My problem rewritten says the probability of even number or a number greater than 4. So for the probability of A, I'm going to change that part of the problem to the probability of getting an even number. For the probability of B in the formula, I'm going to change that to the probability of getting a number greater than 4. And the formula to the right of the equal sign has 3 parts. And I need to get all 3 parts in, and I don't really have room for it. So to find the probability of getting an even number or a number greater than 4, I'm going to find 3 probabilities. The first probability is the probability of getting an even number. And when I roll a single dice, I need to know the sample space to compute probabilities. When you roll a single 6-sided dice, the sample space has 6 numbers in it. So when I compute probabilities, each is going to be a fraction with a 6 in the denominator. For the first probability, the probability of getting an even number, well, the even numbers are 2, 4, and 6. So the probability of getting an even number will be 3 and 6. So I went from generic formula, tailored the formula to my problem, and now I'm going to compute 3 probabilities because the formula requires me to compute 3 probabilities. The probability of A, which is the probability of getting an even number, the probability of B, which is the probability of getting a number greater than 4, and then the probability of A and B happen simultaneously, which is rolling an even number that's rolling a number that's even and greater than 4. So probability of getting an even number is 3 and 6. The probability of getting a number greater than 4, is that would be getting a 5 or a 6 because those are the two numbers that are greater than 4. So the probability of getting a number greater than 4 is going to be 2 and 6. So I've figured out the probability of getting an even number, the probability of getting a number greater than 4, and lastly I want to find out the probability of getting simultaneously one number that's both even and greater than 4, and that's the intersection between the two events. So the first event, A, had 2, 4, and 6 as successes. The second event, B, had getting a 5 and a 6 as a success. Well, A and B together, the only thing that satisfies both of them, that is both an even number and a number greater than 4, is getting a 6. So the probability of A and B happening together would be 1 in 6, because there's one number that's both even and greater than 4. If I do this computation, it'll give me the answer to the problem. So I'm going to go 3 and 6 plus 2 and 6 minus 1 and 6 equals 3 plus 2 minus 1 over 6, because if fractions are being added with the same denominators or subtracted with the same denominators, the denominators don't change, the enumerator does. So this is 3 plus 2 is 5 minus 1 is 4. So you get 4 over 6, which is 2 over 3. In some sense, this is the entire section. Every section in this problem, every problem in this section is going to have a probability question that's an OR probability question, which means we're doing one experiment, and this experiment will be deemed successful if one or another event happens. And I'm going to use this formula to solve every problem, even though I can do the problems without the formula. Like I said, I've had really bad luck doing the problems without the formula. So here's another example. We take the numbers 1 through 10, we throw them on a piece of paper, and throw those pieces of paper into a bucket. One piece of paper is taken out. This is probably important because this is a single experiment. My single experiment is pulling one number from the bucket. And the question is, what is the probability that the piece of paper has an even number or a number greater than 6 on it? So this is, again, a classic OR problem, because I'm doing one experiment, I'm pulling one number from a bucket, and it's an OR problem because I'm trying to find the probability of one event or another event. Easy enough to do, so now I need to define my two events. So to the left of the word OR, the event that's described is rolling an even number. I'm going to call that event A. So event A is selecting an even number. To the right of the OR, the words after it, I'm going to make those event B, and that's going to be getting a number greater than 6. So I have event A getting an even number, event B getting a number greater than 6. So now I'm going to change my formula. The formula generically is this, and I'm going to change A to selecting an even number. I'm going to leave the word OR. I'm going to make B getting a number bigger than 6. Now the formula requires me to separately do A and B, so I'm going to do the probability of A, which is the probability of getting an even number, and to do the probability of A, so what the sample space here, what can be selected is any number between 1 and 10. And so the probability of A, because A is getting an even number, is going to have a 10 in the denominator, because there's 10 different numbers that could be selected. And for problem A, the numerator is going to be 5 because there's 5 even numbers. For B, the probability of B is also going to have a 10 in the denominator because there's 10 numbers in the sample space. And to do the probability of B, I have to count all the numbers in the sample space that are greater than 6, but not equal to 6. So the probability of B is going to be 4 out of 10 because there's 4 numbers in the sample space that are bigger than 6. The last part of the formula requires me to find the probability of A and B occurring simultaneously. And the way I did the sample space this time, you could see it really clearly. When I did the probability of A, I marked these items in the sample space in pink. When I did the probability of B, I marked the sample space items in blue, and any item that's in both pink and blue satisfies both A and B, and that's the items I need for the probability of A and B. So for the probability of A and B, there are two items or two elements in the sample space that fit that they are even and they are greater than 6. So the probability of A and B happen simultaneously is 2 and 10. So I did my 3 probabilities, and now I'm going to simplify. So this is going to be 5 plus 4 minus 2 over 10. 5 plus 4 is 9, 9 minus 2 is 7, and now we get 7 over 10 for that. So once we get through a few of these, they start to get easy-ish, hopefully. So, example. So this is probably more examples than I might do in another section, because we're going to do a lot of word problems too, but I just wanted to do a lot of examples. So same problem. We're pulling a number out of a bucket that has the numbers 1 through 10 in it, but different or probability question. So I'm going to reproduce this sample space. So when I pull a number from that bucket, I can get any number between 1 and 10. They're all equally likely. I'm pulling one number from that bucket, and in this problem I'm trying to find what's the probability that I get a number less than 5 or a number greater than 8. So let me try to do this in events. So I look to the left of the word or, and the event that's described to the left of the word or is getting a number less than 5. So I'm going to call A the event of getting a number less than 5. After the word or, I see the getting a number greater than 8. So I'm going to let B be the event of getting a number greater than 8. So for my probability of A or B, it's going to be the probability of getting a number less than 5 or a number greater than 8. So A is going to be getting a number less than 5. B is going to be getting a number greater than 8. And A and B would be getting a number that's both less than 5 and greater than 8. So now let me figure out A in my sample space. So A, the probability of A is going to have a denominator of 10 because there's 10 items in the sample space that I could pull from. And to get a number less than 5, that would be getting a 1, 2, 3, or 4. 5 is not less than 5. So the probability of A is 4 in 10. B is getting a number greater than 8. And for B, the numbers greater than 8 that aren't equal to 8 are 9 and 10. So the probability of B is 2 in 10. And lastly, I need to find the overlap for the probability of getting a number that's both less than 5 and greater than 8. Well, the way I constructed the A and the B numbers, there aren't any overlap. So there isn't any number that's both less than 5 and greater than 8. So there aren't any numbers to count for the probability of A and B. So the probability of that happening is 0 and 10, because there isn't any number that is simultaneously less than 5 and greater than 8. It's impossible to get one number and have it both be less than 5 and greater than 8. So my probability is going to be 4 in 10 plus 2 in 10 minus 0 in 10, which is 4 plus 2 minus 0 in 10, which is 6 in 10, and 6 in 10 reduces to 3 over 5. The reason this problem is in here is because I wanted to talk about a word that we don't really need to know, but it's probably nice just to mention. So in this problem, because the probability of A and B happening together, the fact that there is no number that's both less than 5 and greater than 8, when the probability of A and B is 0, them happening together, we say the two events are mutually exclusive. That is, if it's impossible for both events to happen simultaneously, those events are called mutually exclusive, which means if one happens, the other can't happen, essentially. And in mutually exclusive OR problems, you don't really have to do this piece because that piece is 0. but I'll ignore that as I do the problems, because the formula's going to work every time, and I don't have to worry about whether something's mutually exclusive or not. It'll come out as I do the problem. But when you are doing or mutually exclusive problem, you don't have to do the subtraction part, but I'm going to do it anyways. All right, so deck of cards. So I brought my deck of cards today, and I'm really not that excited about this problem, but I'll live with it. So this is, well, I'm trying to make it easier, but I almost think I feel like I'm making it harder. So let me change my problem to make it more like yours, and then explain these problems the best I can explain these. So I'm defining two events. So I'm trying to create a probability question that's using the formula. That's not a word problem just yet. I thought we'd kind of step into the word problems, but I almost think that it's probably a little bit harder. So I'm going to create two events. A is going to be the event of getting a queen. B is going to be the event of getting a king. And I want to find the probability of A or B. Well, I know from the formula that so I'm assuming one card is being selected from a deck of cards, and I'm trying to find the probability of event A or the event B. So it's an or probability problem. And to find the probability of A or B, I have to attach words in place of the A and words in place of the B. So the probability of getting a queen or a king is what the probability of A or B is in this particular problem 2, at least my modified problem 2. And by my formula, the probability of A or B is the probability of A plus the probability of B less the probability of A and B. I can solve this problem. So I'm going to solve this problem by changing the probability of A or B to the probability of getting a queen or a king when you select one card from a deck of cards. And now I'm going to break that into the right side of the formula and work on that. So this is going to be the probability of getting a queen plus the probability of getting a king less the probability of getting a card that's both a queen and a king. And I brought my sample space with me because it's easier to do with marking up a sample space. So now I'm going to do the probabilities. The first probability I'm going to do is a probability of getting a queen. I'm pulling one card from a deck of cards, so the denominator is going to be 52 because there's 52 cards that I could get. So the probability of getting a queen is going to be 4 and 52 because there's 4 queens in a deck of cards. So now I can replace the probability of getting a queen to what it equals to 4 and 52. I can reduce it, but I'm going to hold off on the reducing just in case I need that denominator of 52. The next probability I need to compute is the probability of getting a king, and the probability of getting a king is going to be the same 4 and 52 because there's 4 kings in a deck of cards. So I've done 2 of the 3 probabilities. The last probability is the probability of getting a card that's simultaneously a queen and a king, and the number that would go in the numerator is the number of overlapping numbers or cards. There is, for the queens and the kings, there's no commonality, so there's no card that I've marked with both pink and blue. So it's impossible to get a card that's both a queen and a king. So the numerator for this problem, for the probability of getting a card that's both a queen and a king, is going to be 0 because there's no card in a deck of cards that's simultaneously a queen and a king. These are mutually exclusive events. If you get a queen, it can't also be a king. If you get a king, it can't also be a queen. So the probability of getting a queen and a king is 0 and 52. Now I'm going to add 4 plus 4 minus 0 and divide by 52. And my answer in a non-reduced form is going to be 8 over 52. And then if I was feeling lazy this morning and wanted to reduce this on my calculator, I could just go 8 divided by 52 and then math, enter, enter. And the answer to this problem number 2 is going to be 2 and 13. So for number 2, at least the modified version of number 2 to make it more like your problem number 1, the probability of getting a queen or a king is 2 and 13. So problem 4 and 3 should have the same question. I'm picking one card from a deck of cards. I'm told what the A and the B are. I'm trying to find the probability of A or B. And let's see what I can do with mine. Yeah, they're good problems. They work together nicely. So for my problem, I want the probability of getting, so I'm going to do number 4, a picture card, which is a jack, queen, or king, because I have pictures of faces on them, or a red card. And that's going to equal the probability of getting a picture card plus the probability of getting a red card less the probability of getting a card that's both a picture card and red simultaneously. So I'm going to do 3 probability computations. And because I'm just picking one card from a deck of cards, each of the denominators is going to be 52 because there's only 52 cards in a deck of cards. So first probability, I'm going to do my picture cards. And the picture cards that I have are these. The jacks, the queens, and the kings are called picture cards. So for this problem, I'm highlighting in blue the picture cards, or emphasizing in blue the picture cards. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 picture cards. So the probability of getting a picture card is going to be 12 and 52. So that's the probability of A. A is getting a picture card. The next probability I want to do is the probability of getting a red card. Well, the red cards are the hearts and the diamonds, and the hearts and the diamonds are down here on mine, so I'm going to highlight every heart and every diamond and count how many cards I'm highlighting. So I've highlighted all the hearts and the diamonds. There are 13 hearts and 13 diamonds. If you count all the cards that I just highlighted in pink, you'd come out with 26 cards. So the probability of getting a red card is going to be 26 and 52. That's the second probability. The last probability is the probability of getting a card that's both a picture card and a red card, and that's the cards that have both blue boxes around them and pink highlights. That's these 6 right there. Those 6 cards fit both criteria. They're a red card because they're highlighted in pink, and they're a picture card because they've got a blue box around them, and there's 6 of those cards. So the numerator of this fraction is good. The last fraction is going to have 6 and 52. So now for my probability, it's going to just be 12 plus 26 minus 6 over 52, and that's 32 over 52, but I'm afraid that I'm messing up, so I'm going to do it all on my calculator. I'm going to go 12 plus 26 minus 6 divided by 52, so I did the whole problem all in once. Enter, and then math, enter, enter, and my answer is going to be 8 and 13. So without really fussing with reducing fractions and doing any math in my head, I can get the answer. It's probably what I'd kind of expect you to do, just because it's safer to do that than it is to do it in your head. The next few problems, they're not really from the examples, but they're applications of using the formula, and I just I needed to do them, and I just put them at the beginning just to get them done because they're not that hard. So 5 through 8 I didn't do an example for because I didn't think we needed an example. I thought I could do them just with the problems, and I can't imagine putting 5 through 8 on a test, but it's something I'm required to teach, so I teach it. So I'm going to use this formula, and in a non-word problem sense, I'm going to manipulate the formula. So in problem 6, I'm given a few pieces of information. I'm given information that I can shove into the formula. I'm given the probability of event A is 0.6, which is 60%. The probability of point B is 0.8, which is 80%. And the probability of A and B equals 10%. And I was asked to find the probability of A or B. Each of the next 4 problems just want me to use the formula. So the formula, probability of A or B equals the probability of A plus the probability of B less the probability of A and B can be used to solve the problem because it's super easy. So I'm trying to find the probability of A or B, so that symbol I'm not going to replace a number. The other 3 symbols can be replaced by the numbers that they're equal to in this problem. So I'm going to leave the symbol that I'm trying to find unchanged, and I'm going to replace the next 3 symbols with numbers. So for the probability of A, I'm going to change that symbol to the number 0.6. I'm going to leave the plus sign between the probability of A and the probability of B. For the probability of B, I'm going to change that symbol to 0.8, leave the minus sign, and for the probability of A and B, I'm going to change that symbol to 0.1, and I'll get the answer. The probability of A or B equals, I think it's, well, this is an impossibility. Make sure this is right. The problem's bad because probabilities can't go over 1, and this is going over 1. So let me change this probability to 0.5, sorry, and change that probability to 0.5. You would probably never even realize that that's a mistake, but probabilities have to be between 0 and 1. I started doing the math in my head, and when I made up a problem, the numbers didn't feel bad to put in, but they are bad to put in. Sorry again for that. This is the first time I'm doing the even problems. I've done all the odd problems a bunch of times, but the even problems I haven't. So let me just do this. 0.6 plus 0.8 less 0.5, and I'll get 0.9. So the probability of A or B is 90%, which is 0.9. That's the answer to the modified problem 6. Hopefully changing that on the fly didn't kill you. Again, can't imagine putting these on a test. So, good. Is that okay? I'm trying to make sure this is okay all of a sudden. So, for 8, I'm going to do the same thing. I'm going to use the formula, and in this problem, the information that's given to me is the probability of A or B equals 0.6. The probability of B equals 0.3, and the probability of A and B, which kind of, when I blew up the font, it kind of got messed up, but the probability of A and B is 0.1. I'm trying to find the probability of A. And again, I'm just going to use the formula and plug the numbers that are given in the formula. So the formula is the probability of A or B equals the probability of A plus the probability of B less the probability of A and B. And for the probability of A or B, I'm going to put 0.6. I'm trying to find the probability of A, so I'm going to leave that symbol intact. For the probability of B, I'm going to put 0.3. For the probability of A and B, I'm going to put 0.1. Now I'm just going to do a bit of algebra. I'm going to subtract those. 0.3 minus 0.1 is 0.2. So I'm going to get 0.6 equals the probability of A plus 0.2, because 0.3 minus 0.1 is 0.2. If I did 0.3 minus 0.1, my calculator would give me 0.2, and you don't need the 0 there, but it's okay to have it there. And then to finish off solving for the probability of A, I'm going to minus 0.2 on both sides. On the left side, 0.6 minus 0.2 is going to be 0.4. On the right side, the 0.2's cancel. I'm left with the probability of A. So the answer to problem 8 is the probability of A is 0.4, or 40%, or 4 over 10, or 2 over 5. But this is all that this problem wants. So hopefully you can do problems 5 and 7 with that as a kind of a basis. Now we're going to get into probabilities that are more like the examples. So problems 9 through 12 is an experiment that we did a few examples with. A single 6-sided dice is rolled. So the sample space of rolling a single 6-sided dice is, you can get any of the numbers between 1 and 6. I'm going to do 10, and 10, the probabilities that I'm comparing is getting an even number or a number less than 5. So I want to do the probability of getting an even number or a number that's less than 5. And that's going to equal to the probability of getting an even number plus the probability of getting a number that's less than 5 minus the probability of getting an even number and less than a number that's less than 5. So I need to do 3 fractions. Each fraction is going to have a 6 in the denominator because the sample space has 6 items. So first I'm going to do the probability of getting an even number, and the even numbers in my sample space are 2, 4, and 6, so the probability of getting an even number is 3 and 6. Next I'm going to do the probability of getting a number less than 5. The numbers that are less than 5 are 1, 2, 3, and 4. So the probability of getting a number less than 5 is 4 and 6. And then I want to subtract out the probability of getting a number that's both even and less than 5. And when I mark up my sample space this way, you can see how many there is. There are 2 numbers, the numbers 2 and 4. They're even and less than 5. So I need to subtract out that 2 and 6 fraction. Now I just add and subtract. Simplify the fractions. I get 3 plus 4 minus 2 over 6. And my answer to problem 10, the probability of getting an even number or a number less than 5 is going to be 5 and 6. So it's just a matter of, if you can get a sample space, it's just a matter of marking up the sample spaces to get the individual probabilities and using the formula. So your problem 9 should work almost exactly the same way, other than you're looking for a number greater than 2 and an odd number instead of an even number, but it's kind of the same. Really? Let me change mine again. How about that? I'm going to do a number greater than 5 or less than 4. As it was kind of odd, and it wasn't enough like your problem. So I modified mine on the fly again. I'm doing these even problems kind of for the first time. And when I wrote the problems, I kind of thought they were better than they were, some of them. So for problem 12, I want to find the probability of getting a number greater than 5 or less than 4. And I'm going to do 3 probabilities. The probability of getting a number greater than 5 plus the probability of getting a number less than 4 less the probability of getting a number that's both greater than 5 and less than 4. So I use words and symbols. You can use either. So let me create a sample space. The sample space of rolling a single dice has the numbers 1 through 6 in it. For getting a number greater than 5, there's only one number greater than 5. So the probability of getting a number greater than 5 is going to be 1 in 6. For a number less than 4, the numbers that are less than 4, not including 4 because it doesn't say less than or equal to, are the numbers 1, 2, and 3. So the probability of getting a number less than 4 is going to be 3 in 6. And then the fraction that I need to subtract out isn't going to have anything in the numerator. It's going to be 0 in 6 because there's no number that's simultaneously greater than 5 and less than 4 because there is no overlap between the numbers that qualified for greater than 5 and the numbers that qualified for less than 4. So that numerator is going to be 0 because there's no number that's simultaneously circled in black and pink. So this is going to be 1 plus 3 minus 0 over 6. That's going to be 4 and 6. And my answer to problem 12, the probability of getting a number greater than 5 or less than 4 is going to be 2 and 3. Now we get to the world of cards. Jack or diamond. How about this? Again, I'm trying to make mine more like yours than they are. I do. That seems fine. So I'm modifying my problem 14 to be just like your problem 13, or enough like it. So one card selected from a deck of cards, find the probability of getting a jack or a diamond. So I'm picking one card and it's an orb probability, so I can use the formula. So the probability for my problem 14, my modified problem 14, of getting a queen or a red card equals the probability of getting a queen plus the probability of getting a red card less the probability of getting a card that's both a queen and red. Each one of these is going to be a fraction that has a 52 in the denominator because when I'm picking one card from a deck of cards, the denominator is 52 because there's 52 cards in a deck of cards. So now I'll work on the numerators. For the queens in a deck of cards, there are 4 queens. So for the queen probability, I'm going to write 4 over 52 because there's 4 queens in a deck of cards. Hopefully you can tell that those are queens. Let me blow this up just a little bit. Not that that probably helps that much. So for the first fraction, the probability of getting a queen, it's going to be 4 over 52. And then for the probability of getting a red card, the hearts and the diamonds are red cards. There's 13 hearts and 13 diamonds. So I'm going to wind up marking off 26 cards. And the numerator for the probability of a red card is going to be 26 and 52. So for the next fraction in my computation, the probability of getting a red card is 26 and 52. And lastly, I need to subtract out any duplication between the probabilities. And there's overlap between queens and red cards. There's 2 cards that I've counted in both sets, the queen of hearts and the queen of diamonds. So for the third fraction, its numerator is going to be the 2 cards that were counted essentially twice, counted in both sets. So the probability for this is going to be the probability of a queen plus the probability of red card less the probability of both a queen and a red card. That's going to be 4 plus 26 minus 2 over 52. And again, I can be just mindless right now and do parentheses 4 plus 26 minus 2 divided by 52 and then math enter enter. And my answer is going to be 7 over 13. but I could have done it by hand. I could have got 28 over 52, because that's what this comes out to be. And then 28 over 52 reduces to 7 over 13. But I didn't care to do the arithmetic in my head because I was worried I was going to make a mistake. So the answer to problem 14 is 7 and 13. So 15 and 16 kind of work similarly. So for 16, I'm trying to find out the probability of getting a queen or a 2. That's going to equal the probability of getting a queen plus the probability of getting a 2 less the probability of getting a card that's both a queen and a 2. So I'll mark up my sample space. The probability of getting a queen is going to be 4 and 52 because in my sample space there's 52 cards and 4 of them are queens. So the first fraction I'm going to get is going to have a 4 over 52. And then I'm going to find the probability of getting a 2. And for a 2, it's the same 4 and 52 because there's 4 2s in my deck of cards. For the last fraction, the two sets are disjoint. There's no card that satisfies both the criteria of being a 2 and a queen. So the numerator for the last fraction is going to be 0 over 52. So I'm going to get 4 plus 4 minus 8 minus 0 over 52. And for an answer, I can do this on my calculator, but this is 4 plus 4 minus 0 over 52. That's 8 and 52. And when you divide by 4, you get what? 2 and 13. But again, I'm going to be dumb and do this on my calculator. So 4 plus 4 minus 0 divided by 52 equals math, enter, enter. And I get 2 and 13 for an answer. So our cards work kind of the same here. So for number 18, the probability of getting a black card or a queen is the probability of a black card plus the probability of queen less the probability of the cards both black and a queen. So for my black cards, I go to my deck of cards, and my black cards are my clubs and my spades. So for the probability of getting a black card, that's all these. Clubs and spades are black. And there's 13 cards in each suit. If you count up the cards that I just highlighted, there's going to be 26 cards that I just highlighted. So for the probability of getting a black card, it's going to be 26 and 52 because there's 26 black cards out of the 52. For a queen, there's 4 queens in a deck of cards, so the queen probability is going to be 4 and 52. And then the and probability, there's 2 cards that are qualify as being black and queens. So I've counted those twice, and that's going to be the last fraction. The probability of getting a card that's both a queen and a black card is 2 and 52. So this is going to be 26 plus 4 minus 2 over 52. Feels like I just did the same probability. And on my calculator now, so clear. 26 plus 4 minus 2 divided by 52. Enter. Math, enter, enter, and I get 7 over 13 for problem 18. Your answer should be similar. I think it's exactly going to be the same answer for number 17. I don't have many sheets of paper left, so we're getting close to the end. Okay, so now I need to make a new sample space. I'm picking one marble from a bag that has 4 reds. So my bag has 1, 2, 3, 4 reds, 5 whites, 6 blue, and 2 yellows. So I have a bag of marbles. I'm going to pick one marble, and I want to find the probability of getting a red or a blue for number 20. So the probability of getting a red or a blue equals the probability of getting a red plus the probability of getting a blue less the probability of getting a marble that's both red and blue. So each of the denominators is going to be how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Each of the denominators is going to be 17 for my fractions because there's 17 marbles in this bag. So for the probability of a red, there are 1, 2, 3, 4 red marbles. So the probability of getting a red marble is 4 in 17. For the probability of getting a blue marble, there's 1, 2, 3, 4, 5, 6 blue marbles. And for the probability of getting one marble that's both red and blue, well, there's no overlap between the highlighted and the circled items in the sample space, so there's no marble that qualifies for being both red and blue, so that fraction has a 0. And so this is just going to be 4 plus 6 minus 0 over 17. I could do that without my calculator because it's a fraction that doesn't reduce. So that's going to be 10 and 17. The worst part of this is creating a sample space, I think. So my sample space, again, is red, 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 4 reds, 5 whites, 6 blues, and 2 yellows. I'm picking one marble out. It's an OR problem because I'm only picking one marble, and it's an OR right in the problem. So the probability of getting a yellow or a blue equals the probability of getting a yellow plus the probability of getting a blue less the probability of getting a marble that's both yellow and blue. Each of the denominators of the fractions are going to be 17 because I'm picking one marble out of the 17 marbles. For the yellow, my numerator is going to be 2 because there's 2 yellow marbles. For the blue, my probability is going to have a 6 in the numerator because there's 6 blue marbles. And for the last probability, there's no overlap between the yellow and the blue when I created to make the numerators. So again, there's going to be a 0 there. So this is going to be 2 plus 6 minus 0 over 17. And my answer to problem 22 is going to be 8 and 17. It's kind of a nice problem because there can't be any overlap because the marbles aren't multicolored. All right, 23 through 26, and that might be the end. No, we've got a few more, but nothing too crazy. So the numbers 1 through 14, I don't know why 1 through 14, are placed on a piece of paper and put into a bucket. So I'm creating my sample space because if I have my sample space, I can do these problems or problems cleanly by just marking up the sample space. Wish I didn't go to 14, but I did. So for 24, I want to get probability of even or a number less than 8. So the probability of even or less than 8, that's going to equal to the probability of getting an even plus the probability of getting a number less than 8 less the probability of getting a number that's both even and less than 8. So each fraction is going to have a 14 in the denominator because there's 14 elements in the sample space because I'm taking the numbers 1 through 14 and put them on slips of paper. That represents the slips of paper. for the evens, there are 1, 2, 3, 4, 5, 6, 7 evens. And then for less than 8, 7 is the first number that's less than 8. There's 7 numbers that I just circled. And then for the both, the 2, the 4, and the 6 have both circles and pink highlights, so they classify as even and less than 8. I'm going to subtract those out. And now I'm going to go 7 plus 7 minus 3 over 14. That's 11 over 14. I can do that without my calculator. So the answer to 24 is 11 over 14. I need to create that sample space again to do 25 and 26. Notice I'm maybe getting lazy and not putting the sample space in set brackets. It hardly matters for this problem. So I want the probability of getting a number less than or equal to 8 or odd. That's going to be the probability of getting a number less than or equal to 8 plus the probability of getting an odd number less the probability of getting a number that's both less than or equal to 8 and odd. So for less than or equal to 8, I have to count the 8. So the first fraction for the less than or equal to 8 is going to have an 8 over 14. It's over 14 because there's 14 elements in the sample space, and the numerator counts the 8 numbers that are less than or equal to 8. Next fraction, I'm counting the odds. I'm circling up the odds in the sample space. And I circled 1, 2, 3, 4, 5, 6, 7 odds. So the probability of getting an odd is 7 and 14. And then I need to subtract out the overlapping. The 1, the 3, the 5, and the 7, which are 4 numbers, they had both categories. They're both less than or equal to 8 and odd, so they need to be subtracted off. And now I'm just going to go 8 plus 7 minus 4 over 14. I think that's 11 over 14. One more set of problems, and it's a little bit different, but it's not really different. It requires some English skills, I guess, that maybe we don't want to have right now. So the letters of the word Mississippi are placed in pieces of paper and thrown into a bucket, and one letter is pulled out. So my sample space are the letters in Mississippi that get tossed into a bucket. And I think there's 11 letters here. Yes. So for my probabilities, each denominator is going to be 11 because I took 11 letters and threw them into a bucket, and I'm pulling one out. The denominator is going to be 11 because there's 11 letters to choose from. So my 28, what is the probability that I get a vowel or the letter M? Well, that's going to equal to the probability of getting a vowel plus the probability of getting an M less the probability of getting something that's both a vowel and an M. So first I'll do the vowels. The vowels are just the I's, I guess. So the probability of getting a vowel is going to be 4 in 11. The probability of getting an M is 1 in 11 because there's only one M. And the probability of getting a vowel and an M is 0 over 11 because there's no overlap between these two vowels and M's. So this is going to be 4 plus 1 minus 0 over 11. And my answer to 28 is going to be 5 over 11. So you should be able to do 27, and the next page is going to have the last problems. Same sample space, dealing with the word Mississippi. So my sample space is M-I-S-S-I-S-S-I-P-P-I. For number 30, I want the probability of getting a vowel, or alphabetically before R, which is going to be equal to the probability of getting a vowel plus the probability of picking a letter alphabetically before R, less the probability of both a vowel and before R. Just crunched down there. So for the vowels, again, the vowels are just the I's. They're the only vowels. The probability of getting a vowel is 4 in 11. And then before R, Q, R, S. The S isn't before R, but the rest of the letters are alphabetically before R. So the M, the I's, and the P's are alphabetically before R. So there's 1, 2, 3, 4, 5, 6, 7 letters that are before R alphabetically. And then the last probability, there are 1, 2, 3, 4 of the letters that fit both. They're vowels and they're before R, so I need to subtract those out. So this is going to be 4 plus 7 minus 4 over 11, and you get 7 over 11. Your subtracting out, I think, is going to be different, but hopefully you can figure it out. So hopefully that wasn't a god-awful lecture. I think eventually I got and I did the problems okay. I'm not so sure that it was the smoothest lecture, but hopefully you can get through the problems with what I did. And if not, again, let me know, and then I'll re-record the video and try to do a better job.